Welcome to section 6.5. We're working with graphs of tangent and cotangent functions in this section. Most of this material, again, is things that you saw in 171. For example, we have a definition here for vertical asymptote. A vertical asymptote is a vertical line that the graph approaches but does not intersect. You saw vertical asymptotes when you worked with logarithmic functions in 171. So let's take a look at the summary of the tangent and cotangent functions. Alright, so the tangent function, if we were to go through and plot all the points in f of x equal tan of x, if we were to put in these x values, we would get these y values. And you'll notice that you're getting these undefined values. Like if you put in negative pi over 2, if you take, or making it even easier, let's say if I want to find tangent of pi over 2. Well, tan of pi over 2, if you think about it, let me grab a sheet of paper real quick. Well, I guess I'll just draw it right here. Tangent of pi over 2, think about your unit circle. Here's pi over 2 up here. Alright, the tangent of this would be, this is going to be 1 over 0, which is undefined. Same thing with negative pi over 2. That brings you down here because you're going to be doing 1 over 0. So you've got those undefined values. Alright, now we've got negative pi over 4 and positive pi over 4. Where is that on our unit circle? Pi over 4 is actually a 45-degree angle right through here. And tangent of the 45-degree angle we know that the ordered pair is square root 2 over 2, comma, square root 2 over 2. Alright, so y over x, that gives us a value of 1. And of course negative pi over 4 would be down here in quadrant 4, and tangent would take on negative values there, so we would have negative pi over 4 and negative 1. Tangent of 0, here, that's going to be y over x, so that's going to be 0 over 1, which gives us our 0. So these are the ordered pairs that we get for the tan function by putting in these values. And so if we were to graph this, first, let's type it into the calculator. So on your calculator, you can go to y equals, and you can type in tangent x. There's your x button, and you can graph it. If your picture does not look like mine, you might want to go back out to Zoom and go to 7 for Z trig, and then you'll have a nice clear picture of what's going on with our function. So this is what the tangent function looks like. It looks like a series of, it looks like the x cubed function from 171, but if it had been flipped across the x-axis, it would look like this. It's like you've got a bunch of upside down x cubed functions, is how it looks. Now the important information that you need to remember about this graph is on your sheet. Remember those undefined values that came from negative pi over 2 and positive pi over 2 on the x-axis. They give us our vertical asymptotes. We have a vertical asymptote when x is equal to negative pi over 2, and we have a vertical asymptote when x is equal to positive pi over 2. That's because the function does not take on any values at those two values of x. And what happens after that is you just get, once you get past this pi over 2 asymptote, which you could see right here on your, oops, I'm sorry, which shows up right here, is a periodic function. So it's going to do the same thing over and over and over again forever in both directions. So what important information do we need to know about this? Well, of course, we need to know where the asymptotes occur. So the graph is discontinuous at values of x of the form x equals 2n plus 1 times pi over 2. That just means that it's going to, the 2n plus 1 just means that it's an odd number. So you're going to have undefined values or asymptotes, for example, at pi over 2, and then at 3 pi over 2, 5 pi over 2, 7 pi over 2. That's what that means. Its x-intercepts have x values of the form n times pi. That just means any integer times pi. So you're going to have an x-intercept here at pi. You'll have one at 2 pi. Then you'll have your next one at 3 pi, 4 pi, 5 pi, etc. The period is pi. Okay, this is important. So the period for the tangent function is pi. So you'll see how if you look at a complete period between the two asymptotes, it starts from negative pi over 2 to positive pi over 2, and that's a distance of pi. There are no minimum or maximum values, so the graph has no amplitude. The graph is symmetric with respect to the origin, so the function is an odd function. For all x in the domain, tangent of negative x is equal to negative tan of x. So this will be imported a little bit later, but for right now, the biggest things that we need to take away from this, we need to know the shape of this. Notice that it increases from the left to the right. It's going up. So you're going to need to remember that about the tangent function, because that's one difference between what we have here in the cotangent function, which we'll talk about next. Okay, so that's what we need to know about our tangent function. I'm going to skip over the cotangent information, and I'm going to come back to that. But let's look at the steps for graphing. All right, so the first example that we're getting ready to do, we're going to be graphing y equals tan of 2/3 x. Okay, so let's look at that really quick. So y equals tangent of 2/3 x. Remember, the 2/3 is your b. So b is 2/3. A, in this case, is 1. All right, and there's no phase shift going on here. You're not adding or subtracting anything from your x. So let's see what the directions tell us about how to graph this. It states that the guidelines for sketching graphs of tangent and cotangent functions to graph y equal a times tan of bx or a times cotangent of bx would be positive. We follow these steps. We determine the period pi over b. So this is going to be something that you've got to remember. So remember, this is a little bit different from when we were doing sine and cosine functions. They had period 2 pi. So whatever function you were working with, you would do 2 pi divided by your b. When you're graphing tangent and cotangent, you need to find, to get your period, it's going to be pi over b now, because our period is pi for the original tangent functions. So we locate two adjacent vertical asymptotes, solve the following equations for x. So for y equal a times tan of bx, so for the tangent function, which we're going to do in example 1, we have to solve b times x equals negative pi over 2 and b times x equals positive pi over 2. This will tell us where our asymptotes are going to end up. Once we know where the asymptotes are, you can just, after that, the asymptotes are really the only thing that you don't really see when you graph it on your calculator. The rest of it, you just can kind of just sketch it right in. You don't need a whole lot of information beyond that. But step 2, they say sketch the two vertical asymptotes. Step 3, divide the interval formed by the vertical asymptotes into 4 equal parts. So that's the same thing that we've been doing. Step 4, evaluate the function and this says the first quarter point, the midpoint, and the third quarter point. In other words, you're going to have 5 key x values, but the first one and the last one are undefined, so you're only having to evaluate it for 3 points. Step 5, join the points with a smooth curve approaching the vertical asymptotes. Indicate additional asymptotes and periods of the graph as necessary. So if you're asked to graph it over 2 periods, for example, then you would have to put in a little more information. Okay, so let's look at example 1. I think we can handle this now. All right, so for example 1, we need to start by finding our asymptotes. So the rule is we're going to solve b times x equals negative, b times x equals negative pi over 2, and we're going to solve b times x equals positive pi over 2, because we know that those are where the asymptotes occur on the original tangent function, as we saw on our paper here. So because those are the original asymptotes, that's what we're going to set b times x equal to this one and b times x equal to this one. Solving for x. In this example, my b is 2/3, so I'm going to have 2/3 x equals negative pi over 2, and 2/3 x equals positive pi over 2. And if I solve this for x, I can cross multiply. So 4x equals negative 3 pi. I then divide both sides by 4, so x equals negative 3 pi over 4. So that would be one of my vertical asymptotes. Over here I'll cross multiply, and I've got 4x equals 3 pi. Divide by 4, so x equals positive 3 pi over 4. Okay, so I've got my asymptotes in, and the next thing they said to do was to divide it into 4 equal parts. So we know we're going to start from negative 3 pi over 4, and we're going to go to positive 3 pi over 4. Halfway in this is going to be 0. And then halfway from 0 to 3 pi over 4, that's going to be 3 pi over 8. And then halfway between negative 3 pi over 4 and 0 will be negative 3 pi over 8. So we can set up our table of values for this. So I'm going to go to my next page. I've still got a little bit of space left to work with there. I'll set up my table. I've got a bad habit, I know, of not giving you guys enough space on your paper, on your notes. Okay, so we only have to put in these 3 because we know these are going to be undefined. Those are going to be asymptotes. So we'll put in negative 3 pi over 8. We'll put in 0. We'll put in positive 3 pi over 8. And across the top, we're going to build the equation that we were given. We were given y equals tan of 2/3 x, so I'm going to first do 2/3 x for my first column. Now, if I put negative 3 pi over 8 in here for my x, that would give me negative 3/8 times 2/3, which is going to be negative pi over 4. If I put in 0 for x, I get 0. If I put in 3 pi over 8 for my x, that's going to give me, the 3's will cancel. Let's see, I've got 2/3 times 3 pi over 8. So you can see how the 3's are going to cancel, and the 2 and the 8 gives you a 4 in the bottom, so you get positive pi over 4. Okay? Now remember in the sine and the cosine functions how that first column always gave us all of our quadrantal angles? Okay, that's not happening with the tangent function, but that's okay. Alright, so now we're going to do tan of what we just found, tan of 2/3 x. Alright, so tangent of negative pi over 4, that would be tangent of negative 45 degrees, is what that's saying. Alright, so that's going to put you in quadrant 4, so you're going to have a negative value. And tangent of 45 degrees, we know that's 1. Alright, tangent of 0 is 0, and tangent of pi over 4 is positive 1. So those are the values that we need to graph it, and I think I've got enough space I can get it in over here. So we'll first put in our asymptotes. So we know that the asymptotes occurred at negative 3 pi over 4. So just draw that in and label it. And we had one at positive 3 pi over 4. Okay, and then we've got these values at negative 3 pi over 8, y is equal to negative 1. So I'm going to label it like this. At x equals 0, y is 0. And when x equals positive 3 pi over 8 here, y is positive 1. Okay, and then just make sure you're not connecting this with a straight line. It has to be a curve, so it's going to look like this. And over here it's going to come down like this. Again, and it should look like that x cubed function just flipped upside down. No, I'm sorry, this one's not flipped upside down. This is just a regular cube function. I'm sorry. It looks like a regular cube function. Alright, and that's my graph for that one, so that's all I have to do. Let's look at example 2. Example 2 is also a tangent function, so we can continue with the same steps that we did for example 1. Alright, in example 1, excuse me, in example 2, we need to start by setting 2x equal to pi over 2, and we need to do 2x equals negative pi over 2. Okay, solving for x, we're going to get 4x equals pi. So x equals pi over 4. So this is convenient. We're getting the same asymptotes that we had in the last one. And then we'll cross multiply 4x equals negative pi. So x equals negative pi over 4. And we have to divide it up into the same 4 intervals that we did in example 1. So it's going to give us the same thing again. So we can go ahead and set up our table using those same key x values that we had in the first example. So we've got negative pi over 4, negative, is that what I'm sorry, maybe that's not what it was. I'm sorry, it's not. It was negative 3 pi over 4, excuse me. So what's the next one going to be? We know we're going to have one here, 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 and here. So the last one's going to be positive pi over 4. In the middle, we're going to have 0. And in between, we're going to have negative pi over 8 and positive pi over 8. Okay, now we would need to do a column for 2x. So 2 times my x is going to give me negative pi over 2. Oh, I forgot. We don't have to do that one, do we? Because remember, what's that first one, it should give us undefined, but that's okay. If I put in negative pi over 8, I'm going to get 2 times negative pi over 8 gives me negative pi over 4. Putting in 0 for x gives me 0. If x is equal to pi over 8, that's going to give me positive pi over 4. And if x is pi over 4, that's going to give me positive pi over 2. Okay, but again, that first one and the last one should give us undefined values. All right, then we're ready to do the tangent. So tan of 2x for the next column. So what is tangent of negative pi over 2? Well, let's look at the unit circle if you want to. Negative pi over 2 would put me down here. That tangent is undefined, as we expected. Negative pi over 4 is going to put me there at a 45-degree angle. That tangent is going to be negative 1. At 0 degrees, I'm here. Tangent now is going to be 0. And then pi over 4 is 45 degrees. Tangent is 1. And pi over 2, my tangent is undefined. And then, what else do I have left? Go back to the original problem. We need to multiply what we've just done by negative 1/2. Okay, so that's still undefined. That's going to give me positive 1/2, 0, negative 1/2, undefined. And I'm ready to graph it. So my asymptotes occurred at negative pi over 4 and positive pi over 4. And I've got values at negative pi over 8, 0, and positive pi over 8. And my y values are going, this time they're going from negative 1/2 to positive 1/2, so I'm going to label that. I'll call this my 1. This can be negative 1/2 here. So, negative pi over 8 on x, 1/2 on y would put me here. 0 on x, 0 on y puts me here. And positive pi over 8 on x, negative 1/2 on y puts me here. How does this compare to the previous one? Similar to it, but this time it's actually been flipped across the x-axis. And that's not surprising because the coefficient was a negative. So we know that when we have a negative coefficient, just like you saw in 171, that negative in the front does flip it across the x-axis, and that's what happened with this one. But that's what my graph looks like. Now, how much of this can you let the... So I would encourage you to do your table, but the calculator will help you as well. So let's look at how much of this can we get from just looking at the calculator. If I type in, our problem this time was y equals -1/2 times tan of 2x, and graphing that. And I'll do my Z-trig, so when this finishes, go to zoom 7. You'll see how they're closer together this time because the period was shorter. Alright, so this is, so what we've graphed like this much in here. And it is decreasing because it had that negative in the front. So just make sure, no, you don't, again, the thing is you don't have, the calculator's not really making it easy to see where the vertical asymptotes need to be. So you need to make sure that you're able to find the vertical asymptotes, the very first step that we did. But if you can find your vertical asymptote, feel free to look at the graph of the calculator to get a good picture of what should be happening with the shape of your graph. You could be asked to fill in the table, and if you are, you should be able to do that. But you don't have to do it for every single problem. It's okay to let the calculator help you with some of this too. Okay, the next example we're working with cotangent. So let's talk about cotangent. Alright, so the cotangent function, first of all, how do we get that on the calculator? You go to y equals. Remember, there's no cotangent button on your calculator, so you have to remember that cotangent is the reciprocal of tangent. You can get its graph if you just say 1 divided by tangent. And x. And graph. This is our cotangent function. Now, what's happening with this one? Let's look at the information they've given us. They talk about how to plot the points, and you could go through and do that as well. What I want you to recognize here, though, is that this time the period goes from the y-axis over to pi. So you still have period pi, but remember, tangent kind of straddled the y-axis, so it started on this side and went to it went from negative pi over 2 to positive pi over 2. Your cotangent function goes from 0 to pi. So that's one key difference. Also, you'll notice that the cotangent function is decreasing, whereas tangent was increasing. Most everything else is going to be pretty much most stuff is going to be the same. But it is flipped over the x-axis, and it goes from 0 to pi. Alright, so just reading through this really quickly, the x-intercepts are going to be different. Well, let's start here. The graph is discontinuous at values of x of the form x equal n times pi. So that just means that you have asymptotes at multiples of pi. So you'll have so the cotangent function will have a vertical asymptote at pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. Its x-intercepts have x values of the form 2n plus 1 times pi over 2. Okay, so it's like they're flip-flopped. The x-intercepts for the cotangent function are going to be in the same places that the vertical asymptotes were for the tangent function. So this time the x-intercepts will occur at odd multiples of pi over 2. So for example, pi over 2, 3 pi over 2, 5 pi over 2, etc. Those are going to be your x-intercepts for cotangent. The period is still pi, just like it was in the other one. There are no minimum or maximum values, so its graph has no amplitude, so that's the same as tangent. The graph is symmetric with respect to the origin, so the function is an odd function. For all x in the domain, cotangent of negative x equals negative cotangent of x. So that's the same. So really, these three pieces are the same for tangent and cotangent. The difference is where the x-intercepts occur and where the vertical asymptotes occur, and it's also a decreasing function. Alright, now as far as how to graph it, the steps are still going to be the same. only difference is that when you're doing cotangent, because of the asymptotes occur at 0 and pi, you're going to set your b times x equal to 0 and set b times x equal to pi and solve that way. So that's really the only difference between graphing the two. And then, of course, you have to know that it decreases. All right, so in example 3, we want to graph y equals 1/2 cotangent of 2x. So we'll start by setting 2x equal to 0. We'll solve this, and we'll also solve 2x equal pi. So this will give us our vertical asymptotes. So here, divide both sides by 2, we get a vertical asymptote at x equal 2. And over here, divide by 2, we get 1x equals pi over 2. Alright, so I'm going to draw it. This time I'm going to be a little bit lazy and just go ahead and draw it. And we'll see if we have... You may have to do the table. You may not. So let's just see what happens. So we'll put in a vertical asymptote at pi over 2. So let's get our x-axis labeled here. So labeling our x-axis. Our period is pi over b, which is pi over 2 for this problem. And it's going to go from pi over 2 to... Okay, if you would go back and correct when I was solving for the first vertical asymptote, that one is x equal to 0. I divided by 2 and I should get 0 there. So my period is going to go from 0 to pi over 2. And I know it needs to be divided into 4 equal parts, so pi over 2 is going to be all the way down here. And over here will be pi over 4. And this time we're going to let the calculator help us. So we've got the vertical asymptote x equals 0, and then we have one at pi over 2. Okay, so let's go to the calculator and see what it can do for us this time. We're going to type in 1/2. And then for cotangent, we have to do, I'm going to put parentheses, and I'm going to do 1 over tangent 2x, close parentheses. And close parentheses twice because you've got 2 sets this time. And graph that. So we know it's decreasing. And you can probably trace to get some ordered pairs. I'm not sure how well it's going to work on this. I can't really see where the cursor is. There it is. So you can get decimal approximations. It's not the greatest though, but we know that our x-intercept is going to be at pi over 4, and we can see that this one is decreasing, so it's going to look like this for that one period. All right, now what about this point and this point? Well, we could calculate those as well. But the calculator is just giving us decimal approximations. So it kind of depends. If you have to have exact values, then you will probably need to work it out. So we know this point, and we know these are undefined. So how would we get those, that one and that one? So negative pi over 8 here, and then that would be 3 pi over 8 here. So if I need to get 1/2 times cotangent of 2 times pi over 8, and then I'll simplify that. So 1/2 times cotangent of pi over 4, the 1/2 times 1 over tangent of pi over 4 gives me 1/2 times, I know that tangent of pi over 4 is the same thing as tangent of 45 degrees, and that's 1, so that's a 1. So it's 1/2, that's what we're getting for our y values here. Alright, so if that's 1, then 1/2 would be right about there. Like that. And then the other one should be negative 1/2 down here. So that's how you could get those points. But that's what the graph looks like for example 3. Example 4, what's happening in example 4? All right, we're back on a tangent function again. I noticed it's plus 2, so this is the only thing that's happening with this. To me, the easiest way to graph this one is if you go back and just look at your original tangent function. All right, you know that the asymptotes are at negative pi over 2, positive pi over 2, so you're going to take this graph, but you've got this 2 being added to it, so we know that's a vertical shift up 2 units. So we could shift this up 2 units and we'll have our graph. So this one is the easy. I would go with the translations this time rather than the table. So I'm going to start by looking at the original tangent. I'm just going to transfer this graph that I have here onto my paper, but I'm going to use a dotted line because I know I have to shift it. So here's my vertical asymptotes. Alright, and I know that it looks like this. So the original tangent function looks like this. Alright, I'm going to be shifting it up 2 units, so I'm going to put it up here at 2. So my x-intercept has moved up, or excuse me, my y-intercept has moved up to ordered pair 0, 2. And I can draw the same function through here. So that's what this graph looks like. And of course you can get more, it's not hard to find more points if you wanted to fill out your table for this. You would have, oh, and I forgot to label this. This will be negative pi over 4 for the x-intercept. Oh, I'm sorry, not for the x-intercept, but negative pi over 4 for the halfway mark. And then this will be positive pi over 4 over here. So if we put in negative, sorry, this negative pi over 4. I guess some whiteout would help. All right, negative pi over 4. 0, positive pi over 4. Okay, you know that tan of x, we know that that's going to be negative 1, 0, 1, and then if you add 2, that gives you ordered pairs of 1, 0, 3. So that's where we are. Negative pi over 4 would be at negative 1 on the y-axis, so right around here. And then we've got, oh, I'm sorry, I goofed up. That should be a 2. Okay, so x equal to 0, y is equal to 2. And when x equals pi over 4, y is equal to 3. So this would be up here somewhere. And that's example 4. For example 5, we're asked to graph y equals negative 2 minus cotangent of x minus pi over 4. There are different ways that you can approach this. You can go through all the steps that we've done before. You can do the table of values if you want to, if you're comfortable with that. But you can also do the transformations that we've discussed. If you look at this, you'll notice that, first of all, we've got a cotangent function. All right, we've got a phase shift. Well, before I continue, notice, remember, is you're looking at y equals a times cotangent of b times x. That's what we've been talking about today. Okay, b here is actually 1 because there's nothing in front of our x. So our b is 1. We don't have anything multiplied to the rest of the x minus pi over 4 over here. Because b is 1, you can read your phase shift directly from the problem that's given. Our phase shift is pi over 4 units to the right. It's just a horizontal translation. Also, if you know what the cotangent function looks like, it's not hard to get the graph of this problem. The negative 2 in the front, that's telling us that that's a vertical shift down 2 units. And the negative cotangent tells me to take my original cotangent function and reflect it across the x-axis. So we could just do the transformations to get this graph. Just go back and look at your original cotangent function. So we do need to remember that the period was pi, and the vertical asymptotes are at x equals 0 and x equal pi. So I'm going to draw this with a dotted graph, and then I'm going to put my new one maybe in a different color. So let me find, I'm going to start with my blue, and I'll put my answer in red. So just transposing this graph onto my paper. Okay, so I know it's going to go through, my vertical asymptote is at pi for the original function. And I've got a x-intercept at pi over 2. And then we could divide it up into pi over 4. And then if we wanted to put another one over here, it would be 3 pi over 4. Alright, and then this is the original function. This is the original cotangent function, like this. Okay, so I hope you can see that. I think you can see it. So that's what the original cotangent function looks like. Now we want to apply these transformations. So first, that horizontal shift, that is pi over 4 units to my right. So that means that all of my vertical asymptotes need to be shifted over as well. So for my new graph, the original vertical asymptote at the y-axis will come over to the line pi over 4, x equal pi over 4. And then the original asymptote at x equal pi is going to be shifted over pi over 4 units, so that's going to put it over here at 5 pi over 4. Okay, so the red shows me my new asymptotes for my new function. Then we've got the original x-intercept was at pi over 2. Alright, and we know we've got a vertical shift down 2 units, so we need to move it down 2 units, and I need some extra units on my graph. So if I move it down 2 units, starting from here, I'm going to go 1, 2, putting me there. Alright, and then how do I draw my curve? Well, you've got a negative cotangent. Alright, negative cotangent is going to reflect it across, it's going to reflect the original graph across the x-axis. So it's going to flip it upside down, making it shaped like this. And then we'll shift that down to here. So we'll have a graph like this now. Alright. And so really, again, the biggest thing that you need to be able to pay attention to is what's happening with these vertical asymptotes. Once you've got the vertical asymptotes, the calculator can really help you fill in the rest of it. So, but that's what example 5 would look like. In our last example, we're given a graph and asked to determine the equation. For these problems, it is it is possible to have more than one correct answer for these. So it could be that you work through a problem like this and you think your answer is correct and it doesn't match the answer key, but that does not necessarily make it wrong, because the circular functions, there's just lots of different ways of going about these. So you can definitely have a correct answer that is not necessarily the same as someone else's correct answer. Okay, so to approach a problem like this, let's look at the vertical asymptotes. I find that it's, generally speaking, easier to start by looking at the vertical asymptotes. I notice in part A, I have asymptotes at x equal negative pi over 2 and x equal positive pi over 2. And I recall that the tan function also has that feature. Also, the period is pi, okay? So it's looking like a tan function, and it does follow the same pattern as the tan function. The tan function does increase like this one does. So I'm thinking I've got a tan function here. So I'm going to put tan of x to start. Now, comparing this to the original tan function, the only other things that I notice are that we have these points let's see, this would be at pi over 4 for the x, and y is 3. And over here at negative pi over 4, we've got negative 3 down here. Alright, now, the tan function itself, when x is pi over 4, so let's just play with it. If you do tan of pi over 4, Do you remember what that one was? That's the same thing as doing tan of 45 degrees. Tan of 45 degrees is equal to 1. Okay, we have 3. So what does it look like might be happening to this? If you multiply this answer by 3, then you'll get what we have on our graph. So it looks like you've got a vertical stretch happening here, whereas the original would have been back here. Same thing over here. This would have been, this point would have been on there. So this appears to have a vertical stretch by a factor of 3. Let's do the other one just to see what happens. Like if you do tan, let's do tan of negative pi over 4. Okay, that's the same thing as doing negative pi over 4 would be the reference angle for that would be pi over 4 or 45 degrees. But because it's a negative angle, it puts us in quadrant 4. So it's going to be negative tan of 45 degrees, and that gives us negative 1, whereas we have a negative 3. So I think we just need to multiply what we have here by 3 and get y equal tan of x. I'm sorry, y equals 3 times tan of x. Okay, and that is one correct answer for this. It's probably not the only correct one. But y equals 3 times tan of x is what my equation is here. For part B, let's see what's going on this one. Let's look at the vertical asymptotes first. Looks like we've got a vertical asymptote at the y-axis, and then we've got one at 2 pi. Okay, this one more closely resembles the cotangent function. But remember the cotangent function, it went from 0 to pi. So what's happening here with this thing is spread out more. You've got the horizontal stretch, or you could think of it as the vertical, I think we call it horizontal stretch. But you've got, the period is longer than the typical cotangent period should be. So what we need to do is we need to figure out, we're thinking cotangent function just because of the vertical asymptotes starting from 0 and going out this way. So I'm thinking cotangent. But again, you might be thinking something else, and it's okay. But if I think about the cotangent function, but I notice my period is different, how do I figure out what I need to have a b value to get the period where it needs to be? So in order to find b, let's look at, you're going to do, let's see, the rule is to do pi over b okay, so your period is pi over b, and we know that their period pi over b is, our period is 2 pi, so we'll set this up as pi over b equal to 2 pi. Okay, now where am I getting the pi over b? Go back to your rules, your techniques for graphing. To determine the period for the cotangent and tangent functions we were told was pi over b. So I set the pi over b equal to what I see as my period. It goes from 0 to 2 pi. So setting pi over b equal to 2 pi, then if I solve this for b, that gives me the coefficient on x up here. Alright, so to solve this, you can cross multiply. So you would have pi equals 2 pi b, and then divide both sides by 2 pi. That gives me 1/2 for b. So b is equal to 1/2, so 1/2 is the coefficient on my x. So I've got cotangent 1/2 x. Now, what else is happening with this thing? So we've taken care of the period being different from the original period. And if we go to our cotangent function, let's look at it again. Let's compare the pictures. Alright, here's my original cotangent function. This was decreasing. What's happening with ours? Ours is increasing from left to right. So how do we fix that? Just put a negative in the front, and that will reflect it across the x-axis. Is there anything else happening with this? Go back to the original. Alright, look at that original x-intercept. It was at pi over 2. Now, it looks like the x-intercept has been shifted up 1 unit. So if the x-intercept is moving up, that means the entire graph is moving up. It looks like all the original points have shifted up 1 unit, because you can see that point of inflection there has been shifted above the point of inflection. Just means it goes from like a concave down to a concave up. So that's your point of inflection. And that's happening one space above the x-axis where it originally should have been. So that would be that's a vertical translation up 1 unit. So we can fix that over here by adding 1 to our function. So we can say y equals 1. So you're just adding the 1 in the front. And then the cotangent itself needs to be negative. So minus cotangent of 1/2 x. And that is one correct answer that you could have for this problem as well. A negative cotangent is the same thing as a tangent, so you could say it that way also. Alright, but anyway, that finally completes section 6.5, and we will be working on these together soon, and thank you, and good luck with it. I'll see you soon.